This is the Qwen3 235 billion parameter model in Q3 XL quantization, loading on the HP Z2 Mini G1a workstation, powered by the new AMD Strix Halo CPU. Look at that, it's using over 100 gigabytes of memory and it runs pretty smoothly. And this one is the newly released GLM 4.5-Air, another mixture of expert model with 106 billion parameters, of which 12 active, running in Q6 XL quantization. And this one as well runs pretty fast, over 16 tokens per second. Thanks to the new AMD Strix Halo chips, all of this is now possible on relatively affordable hardware, because it has this unified memory architecture that allows the integrated GPU to access the entire system memory up to 128 gigabytes. However, there is a catch. As we'll see, the Strix Halo works best with mixture of expert models like the one I've just shown you, but doesn't do very well with dense models due to its limitations with memory bandwidth. So in this video I'll show you the HP Z2 Mini Workstations with this new chip from AMD and walk you through the setup I am using to get the best performance. Originally, I planned for this to be a very short video, but I ended up learning so much while testing that I decided to document everything and publish a GitHub repo, not only with all the benchmarks that I ran and the configuration tweaks I learned, but also with pre-built toolbox containers that you can use to get the most out of the HP Z2 Mini and really any other machine that uses the same AMD Strix Halo chip. I'll go into the details in the rest of the video, but if you just want the TLDR on how to get this up and running, here it is. First, in the BIOS, allocate the minimum possible amount of memory to the GPU, that is 512 megabytes. Sounds weird, I know, but trust me on this one. Then install a modern Linux distribution with a recent kernel. I tested on Fedora 42 with kernel 6.15.6 and 6.16 and both worked well. Add these kernel parameters to your grub configuration because they are essential to unlock the full unified memory potential of this device. Next, pull the Vulkan RADV toolbox container. It's the most stable and compatible setup. AMDVLK is a faster alternative when it works, but it has limitations where it can't handle certain models when Vulkan buffer allocations need to be larger than 2 gigabytes. RADV doesn't have this limitation, so it's the safest choice. Then create the toolbox, enter it, and list the devices using Llama.cpp list devices. This confirms that everything works and Llama.cpp can see the CPU through the Vulkan RADV driver. Now, to test this out, you need to get a model. I suggest looking up unslot quantized models on Hugging Face. Pick one at the quantization level that will fit in your memory. I'd say anything below 100 gigabytes will work. You can use Hugging Face CLI to download the models. Now that you've got the GGUF weights, let's run the model with Llama CLI. Use NGL 999 to ensure all layers are offloaded to the GPU and use no mmap to prevent some issues with slow model loading. Actually, this is not important on Vulkan, but quite important for ROCm. If you want a web UI, just use Llama Serve and there you go. If you follow this channel, you know that I usually focus on how LLMs work. I've stayed away deliberately from how to run LLMs locally on consumer GPUs because until now the experience has been quite limited, with perhaps the exception of some Apple devices. But on a regular laptop, you are typically restricted to very small 1 to 8 billion parameter models and heavily quantized. And for those of you who haven't heard of this, quantization is basically taking the weights of a model, typically 32-bit floating point numbers, and squashing them down into smaller numbers, like 8-bit, 4-bit, or even 1-bit, so that you can fit them in the memory you have. Of course, this trades quality for space. If you want to learn more about quantization, there's a great video by Julia Turk that I'll link in the description. But realistically, even with an NVIDIA GPU with 8 GB of VRAM that you might find in many laptops, you can really only fit a quantized 8 billion model. For any serious work, these feel like toys compared to what you can get when you access, let's say, GPT-4o via the API. If you wanted a more capable home server, you need something like a desktop with dual NVIDIA, let's say 3090s, giving you 48 GB of total VRAM. Now, that's a step up, but still not enough to run a 70 billion parameter model with reasonable quantization levels. And honestly, building that kind of setup gets expensive fast. You'll be looking at thousands just to get the GPUs, plus you need a beefy power supply, proper cooling. It quickly adds up. For this reason, I've been waiting for the new AMD Ryzen AI MAX, also called Strix Halo. It has a unified memory architecture similar to the Apple's approach with their M-series chips, which allows the integrated GPU to share and access system RAM directly. So it can potentially use the full 128 GB of RAM that it's got available. So I decided I wanted the Strix Halo, but getting hold of PCs with this chip inside has been a bit challenging. I suspect AMD has had delays getting these ready, and many manufacturers haven't had time to design proper systems around it. The first device to ship was the Asus ROG Flow Z13 2025, a 13.4-inch gaming tablet with a detachable keyboard. While it's pretty cool as a concept, it wasn't what I wanted for a mini server use case. It's designed as a portable gaming device with around 110 watt total power consumption and costs around $2,700 for the 128 GB configuration. Plus, I didn't want a tablet or a laptop because the chip's performance is going to be somewhat limited by power usage limits and thermal constraints in that kind of form factor. Really, the first available mini PC with this chip was the EVO X2 from GMKtec. However, it ships from China and there have been reports about quality issues, particularly with cooling. I spent some time on Reddit reading user experiences and it wasn't great. Other Chinese manufacturers have announced similar machines, but they're basically using exactly the same reference board and still aren't shipping in volume. The one I was really after was the Framework desktop because of their reputation for high quality hardware. They've designed their own board and cooling system from scratch, which should deliver much better performances than the Chinese alternatives. But Framework is notoriously slow with product development. I mean, they are a small company doing things right, so it takes time. And they've had to push the release of the Framework desktop towards middle or end of Q3. And this led me to the HP Z2 Mini G1a. It seems to have kind of flown under the radar, but it's been available in the UK for about a month now. The full spec version with 128 GB of RAM is quite expensive on HP's website in the UK, but With HP, you typically want to buy from suppliers rather than direct, as it's always cheaper that way. I found a UK supplier with a very good stock and the price was around £2,300. That's very competitive, even when you compare it with the Chinese GMKtec EVO that actually would have costed me more money here in the UK. Now, the build is what you'd expect from HP. It's a professional workstation, solid and well engineered. No RGB nonsense, just a black box that does its job. The Z2 Mini is remarkably compact, roughly 8 times smaller than a regular desktop tower, while using about half the power. You can open the chassis without tools, which is very nice when you need to access the internals. Now, HP's cooling system uses a high airflow 3D mesh design with sensors to detect thermal load and activate fans preemptively. Here you can see me removing the fan module to install a second 2TB SSD. The whole process took maybe 2 to 3 minutes. I won't go into too much detail about this unit here, but Notebook Check gave it a thorough review, though they focused on gaming benchmarks rather than LLM workloads. They found that the integrated Radeon 8060S GPU performs like an RTX 4070 laptop GPU, and the system handles high CPU loads without thermal throttling. They did mention it gets loud under load, but for LLM server use, you can simply put it in another room like I do. Okay, now for my setup. I've seen reviews of this chip in the GMKtec EVO X2 running Windows, and people were having issues allocating large models, even when they'd set 96 gigabytes of VRAM in the BIOS to the GPU. But since all of this is much more mature on Linux, I decided to install Fedora and test this properly on a Linux system, where you can get the best performance at the moment. The AMD GPU driver on recent Linux kernels has had a lot of development and is getting much better at handling these unified memory setups. With the right kernel parameters, like setting the GTT size to enable unified memory access and disabling the I/O MMU for lower latency, you can actually use up to all of the 128 GB of RAM for model, not just a static portion of it. I decided to test with Llama.cpp, which is the most common tool used for local inference. It's popular because it's written in C++ and heavily optimized. Plus, it supports multiple backends, so you can run the same models on very different consumer hardware. While it can run on CPU, you need GPU acceleration for decent performance, otherwise you're just waiting minutes for each response. Now, before I show you the setup, let me explain what these different backends actually are. For NVIDIA, you'd use CUDA, that's NVIDIA's proprietary compute platform. For AMD, we have several options. First, we have Vulkan. This is a modern cross-platform graphics and compute API. For AMD GPUs on Linux, there are two main Vulkan drivers. We have RADV, and that's the open source Mesa driver developed by the community. It's been around for years, it's stable, and literally it just works. The developers have done an amazing job making it compatible pretty much with everything. Then there's AMDVLK. This is AMD's official open source Vulkan driver. In theory, it should be faster since AMD knows their hardware best. And in my testing, it is faster, sometimes by 30% or more. But there's a catch. Okay, let's look at this. You see, AMDVLK here has a limitation where it can't handle individual Vulkan buffer allocations larger than 2 gigabytes. When Llama.cpp needs to allocate a buffer bigger than that for certain models like this Gemma 3 model, AMDVLK just fails. I've opened an issue on GitHub about this, but until AMD adds support for larger buffer allocations, we're stuck with RADV for these models. The other major option is ROCm. That's AMD's equivalent to CUDA. It's their compute platform for machine learning and HPC workloads. In theory, ROCm should give you the best performance since it's been designed specifically for this kind of work. And for some models, especially those in BF16 format, it does perform really well. But ROCm has its own issues. Let me show you what happens when you try to load a large model without the right flags. Look here at how it's struggling with Llama 4 Scout in Q8 quantization. It does start well, but then becomes very slow. If you want the model to load, you need to disable memory mapping with the no mmap flag. Otherwise, ROCm takes forever to load models over 64 gigabytes. We're talking about hours instead of seconds. Once you know to use that flag, it does work fine. And then there's stability. In my benchmarks, ROCm crashed or hung the GPU many times. Sometimes it works perfectly, sometimes it just doesn't. It is getting better with each release, but still it's not as reliable as Vulkan. To make all of these reproducible, I've created Fedora-based containers using Toolbox. You can pull my pre-built images from Docker Hub and then create the environment with a single command. This way you don't have to mess around with installing drivers, compiling dependencies, and so on. Everything just works. Now, with the system configured, I ran some benchmarks using Llama Bench across all the different backends. Let me show you a quick example of how this works. So, Llama Bench tests two key metrics: prompt processing, and that's how fast the model can read and understand your input, and then text generation, which is how quickly it produces new tokens in the response. Prompt processing affects how long you wait before the model starts responding, while text generation determines how fast the response streams out. Now, let me show you the results. These are from different models across all 5 backend configurations that you find in my Toolbox containers. The results show some really interesting patterns. AMDVLK, when it works, is consistently the fastest, sometimes over 50%. Look at this Gemma 12 billion model. AMDVLK hits 686 tokens per second for prompt processing, while RADV manages 509. That's actually a huge difference. But then look at what happens with some models like Gemma 27B in BF16 format. As we said, AMDVLK can't even load the model. Same for the Kimi 72 billion parameter model. This is that memory allocation bug that I mentioned earlier. So RADV, on the other hand, just works. It might be a bit slower, but it successfully loaded and ran every single model I threw at it. ROCm is interesting. Look at the Qwen models in B16 format. ROCm absolutely crushes it here. We're seeing over 150 tokens per second for prompt processing and 23 tokens per second for text generation. That's 3 times faster than Vulkan for text generation. Now, the likely reason is that ROCm has native support for BF16 through AMD's HIP compute platform, and it's so running closer to the metal. But then, look at the failures. ROCm crashed or hung a lot of times. Sometimes it works perfectly, sometimes it simply doesn't. And you need to remember to use the no nmap flag, or large models will load very slowly. The TLDR here is that you can use the AMD VLK driver as the first option if Llama.cpp can load a model with it successfully. For all other cases, use RADV, and maybe keep ROCm around for specific models with weights in BF16 format, as this is where ROCm currently shines. Those benchmark results show us how fast these models run, but we also need to think about memory requirements. It's not just about having enough memory to load the model weights, you also need memory for the context itself. And depending on what you're trying to do, context size can be really important. For example, having a large context window allows you to analyze long documents, work on large code bases, or maintain extended conversations with the model, like when you're giving it feedback over multiple iterations on a large project. Now, memory usage for context would normally scale quadratically with the number of tokens, and this would end up filling up memory very fast. But most modern models can use flash attention that actually Llama.cpp supports. What flash attention does is make that quadratic scaling much more memory efficient through some computational tricks. But even with flash attention, allowing a large context window takes a lot of RAM. So to help figure out memory requirements for different context sizes, I created a Python script called gguf VRAM estimator. You can just pass it a model in gguf format and it'll give you a table showing you the memory requirements. For example, if we have 128 gigabytes of RAM, we can run Llama 4 Scout with 1 million token context at Q4 quantization. This will just about fit. The model weights are around 58 gigabytes. The 1 million token context adds another 49 gigabytes, and we have a total of 109 gigabytes. However, if we want to run Qwen, the maximum context size we can go with that model is around 131,000 tokens, which would require around 122 gigabytes, really stretching what this machine can do. And you probably want to leave a bit more headroom for the operating system in practice. Of course, you also need to consider prompt processing time. The longer the context, the longer it'll take for the model to respond. Here I'm running Llama 4 Scout in Q4 quantization, and I'm asking a question on a very long document. This is over 100,000 tokens, and as you can see, processing is very slow. Before I wrap up, I want to give credit where it's due. Most of the information about the Strix Halo configurations came from the excellent Strix Halo Home Lab D7 WTF website. There's also a very active Discord community there where people share experiences and help each other out. If you're thinking about getting into these, definitely check it out. I also want to give a shout out to LHL, who maintains the Strix Halo testing repository on GitHub. He was one of the first to experiment with Strix Halo after receiving a test unit of the framework desktop a few months ago. He helped me a lot with understanding the quirks of this platform, and his repository has tons of useful information about different configurations and optimizations. To sum up, the AMD Strix Halo chip is quite capable for running LLMs locally, but it does need a recent Linux kernel and a properly configured environment to reach good performance. The HP Z2 Mini provides a very solid platform for this. With this setup, you can do local LLM work that was previously impractical on most consumer hardware. Is it perfect? Absolutely not. The bandwidth limitations are real, AMD Vulkan has that annoying memory bug, and ROCm still has stability issues. But for the price and power consumption, it's a really compelling option. You're getting Mac Studio level memory capacity at half the price, with the flexibility to run whatever operating system and software you want. I'm planning to do another video on Strix Halo where I'll cover some experiments with training models rather than just running inference. We'll take a small GPT model and pre-train it on the Gutenberg project, and then we will take a larger 7 billion parameter model and fine-tune it for a specific task. If you found this useful, a like helps with the algorithm. Let me know your thoughts in the comments, especially if you've tried similar setups or have questions about specific use cases. Thanks for watching.